You know, when you think of Albert Einstein, you think of a genius who solved it all, right? The guy who completely changed how we see the universe, twice. But what's incredible is that he died with this one giant nagging problem still completely unsolved.
This quote, it just says so much about him. He wasn't just some guy in a lab with equations. He was thinking about humanity, about our future, on this massive scale. He saw the power he was unleashing, and honestly, it worried him. It really sets the stage for the kind of mind we're talking about here.
So that's the big question, isn't it? Why would the man who literally cracked the code of the cosmos spend the last 30 years of his life chasing a problem he just couldn't solve? This wasn't just some side project for him. It was an obsession, a quest that, in the end, he failed to complete.
All right, so here's how we're going to tackle this. First, we'll look at the unsolved problem itself. Then, we'll pinpoint exactly where physics just breaks. We'll dive into the two competing theories, follow Einstein's final quest, see who's on the case today, and finally, figure out why this mystery is so darn hard to solve. Okay, so picture this. In the 20th century, physicists built these two incredible pillars of understanding. Each one is a masterpiece, describing reality with insane accuracy. But there's a huge catch. These two pillars, they just don't get along. In fact, they fundamentally hate each other.
And we're not talking about a small argument here. This is a full-blown crisis, at the most extreme places you can imagine, like inside a black hole or right at the Big Bang. Our two best rule books for the universe completely contradict each other. The math just falls apart and gives us gibberish. It's like our understanding of physics just stops.
So where does this all go wrong? Let's head to what you could call the universe's biggest crime scenes. So, scene number one, the heart of a black hole. General relativity says you've got a singularity in there, a point of infinite density. But quantum mechanics, it sees infinity and just throws up its hands. The math literally breaks. Then you've got the Big Bang. You absolutely need both theories to explain how everything started, but again, they just won't work together.
All right, it's time to meet the two main suspects in this cosmic mystery. So, on one hand, you have general relativity. Think of it like a beautiful flowing river. It's smooth, it's continuous, it's predictable. It describes the big stuff. Then you've got quantum mechanics. That's like looking at the individual water molecules in that river. They're jittery, chaotic, and totally unpredictable. You can only talk about them in terms of probabilities. So, how can the universe be both a smooth river and a bunch of jittery molecules at the same time?
This table really lays out the core of the fight. First up, what even is gravity? General relativity says it's just the curve of space-time. Quantum mechanics says, nope, it's gotta be a particle, a graviton. Total disagreement. Then there's the infinity problem. GR predicts these singularities, but for QM, infinity is like dividing by zero. The whole system crashes. And finally, the math itself is just different. GR's math is for a flexible, changing universe, while QM's math needs a steady, fixed background to even work.
And general relativity, it's just beautiful. It's Einstein's masterpiece. The idea that gravity isn't a pull at all, but the planets and stars are just rolling along these curves in the fabric of space-time, it's just so elegant. And then you have quantum mechanics, the complete opposite. It's bizarre, it's counterintuitive, but man, is it successful. It paints a picture of this subatomic world that's all about chance and probability. You can't say where something is, only where it might be. It's a cosmic lottery. So you have this perfect clockwork universe from relativity versus this chaotic casino universe from quantum mechanics. And Einstein? He hated it. He just couldn't stomach the idea that reality was based on a roll of the dice. That's what kicked off his 30-year obsession to find one single theory that could unite them both.
This timeline is pretty powerful when you think about it. In 1915, he's on top of the world. He's published general relativity. He's the guy. But just 10 years later, he starts on this new path, this search for a unified theory. And for the next 30 years, nothing. It's a story of incredible triumph followed by this long, frustrating hunt.
And this right here, this quote is everything. God does not play dice with the universe. It wasn't just a catchy phrase, it was his whole philosophy. He truly believed that the universe couldn't be random at its core. There had to be a deeper, more predictable set of rules underneath it all.
So how could a mind like Einstein's fail? Well, a few reasons. First, he was basically trying to solve a jigsaw puzzle with huge pieces missing. The strong and weak nuclear forces weren't even known yet. Plus, because he hated the whole probability thing, he was kind of looking in the wrong corner of the room. And finally, the mathematical tools he needed, things like string theory, they wouldn't even be invented for decades.
But Einstein's death wasn't the end of the story. The torch was passed, and now a whole new generation of physicists are on the case, trying to crack this mystery.
For a long time, two main ideas have been leading the pack. First, you have string theory. The idea here is that deep down, every particle is just a tiny vibrating string, like a guitar string. Different vibrations give you different notes, or in this case, different particles. And one of those vibrations would be the graviton. The other big contender is loop quantum gravity. This one's different. It says space-time itself isn't smooth, but it's made of these tiny, indivisible pixels, or loops. So it's a fight. Is the secret in the particles or in the fabric of space itself?
And get this, this isn't some old, dusty problem. The case is hotter than ever. We're talking about major developments happening right now. New theories are popping up, old ideas are getting a second look, and some of them are even starting to look a lot like what Einstein was originally searching for. The chase is definitely still on.
So why is this so hard? I mean, we've had the best brains in the world on this for 100 years. Well, the answer is that the challenges are just on another level.
Okay, look at this number. That's the Planck energy. It's the kind of energy level we need to create in a lab to actually see these theories in action. And that number is just ridiculously, mind-bogglingly huge.
Now look at this number. That's the absolute best we can do today with our most powerful machine, the Large Hadron Collider. The gap between what we need and what we have is, well, it's a quadrillion times. A quadrillion. It's not like trying to see an atom with a magnifying glass. It's like trying to see it from another galaxy.
So that's the bottom line. These are the final walls we're up against. The energy we need is basically science fiction right now. The math keeps giving us these impossible infinity answers. And building something to actually test this stuff, people have calculated that to find one single graviton, you might need a detector the size of Jupiter. So yeah, it's tough.
And so, here we are. A century after Einstein started his quest, we're still staring at the same wall. Will someone come along, a new Einstein, and have a brilliant flash of insight that cracks it all open? Or, and this is the big one, are we just not smart enough? Is it possible the deepest secret of the universe is just beyond what our brains can comprehend? That question about the very limits of our understanding is the real legacy of the problem that even Einstein couldn't solve.